I can't imagine you're listening to all of these, but I hope they're helping, where you get to hear how I'm thinking about these homework problems. Let me know in class. So there are a ton of problems here. You're going to be doing them in class. Hopefully you're not watching this whole thing tonight. Like I said, they're meant to be done in blocks. You'll see kind of similar stuff so that you're reinforcing these ideas. So hopefully you're done with the first block, but let's say you're absent or whatever. We're going to find the derivative of y with respect to x, or even better, we're finding dy dx. And the derivative of e to the x is e to the x natural log of e. We're not going to write natural log of e, but that's pretty useful. The derivative of e to the power 2x, we're going to do the derivative of e to a power is e to that same power. That power is 2x, so chain rule times 2. And then you see, the derivative of e to the 3x, right? We're just thinking, that's going to be e to the 3x times 3. And you might think we have to do something hard here, but we don't. The derivative of 2e to the x is just 2e to the x. That 2 is a constant multiplier. We can just basically ignore it. Okay, so the derivative of 3e to the 4x, we're going to do, e to the 4x has a derivative of e to the 4x times 4, so we'll just do 3 times that 4 is 12e to the 4x. And the derivative of e to the 4th, hopefully you caught it early, is just 0. The derivative of a constant is 0. Back up to the top. Okay. If the derivative of e to the x is e to the x, then the derivative of 2 to the x involves 2 to the x. And don't forget it's 2 to the x natural log of 2, or natural log of the base, because the derivative of 3 to the x should be even easier now that we're thinking about that. 3 to the x natural log of 3. The derivative of 4 to the x is 4 to the power x times the natural log of 4. And the derivative of 5 to the x is 5 to the x natural log of 5. Pattern recognition. All right, block 2. Would it be helpful to have timestamps to jump to each block? I know people on YouTube do that. No idea how. Let me know. Okay, so the derivative of e to a power is e to that same power. This power is x plus 5, which has a rate of change of 1. So we can just write that as e to the power x plus 5. And to me, that's not super surprising because, e to the x looks like this, and e to the x plus 5 is that graph, shifted to the left 5. Okay, so e to the power sine of x is going to have a derivative. Let's leave some room out front. E to the power sine of x times the derivative sine of x. Let's put that out front, cosine of x. The derivative of e to the power cosine x is going to be e to the power cosine of x times the derivative of cosine, negative sine. Now we're getting it. So let's write the derivative of tangent, secant squared, first, and then e to the power tangent of x, because that's probably where our brain is going. The derivative of e to the tangent is e to the tangent. Write that secant squared out front. Okay, now chain rule on 2 to the power. The derivative of 2 to a power is 2 to the power natural log of 2. That power is sine of x, so chain rule times cosine of x. That's probably good enough. The derivative of 3 to a power is going to be 3 to that power natural log of 3 times the derivative of that power. I'm going to put the negative out front and then the sign out back so I don't screw up that negative. All right, the derivative of 4 to a power, maybe I can put that secant squared out front, the derivative of tangent, so 4 to the power of tangent times the natural log of 4. All right, the derivative of e to the power x squared is going to be e to that same power x squared times the 2x. The derivative of 2 to the power x cubed is 2 to the power x cubed, natural log of 2 times the derivative of x cubed, 3x squared. I really don't think we can simplify these. So I know we're supposed to simplify. There really hasn't been any. Okay. I suppose we could, I don't know, put that 3 as an exponent on 2, but that seems crazy. Okay, moving on. Let's see, the derivative of 3 to the power x to the 4th is going to be 3 power x to the 4th, natural log of 3, times the derivative of x to the 4th, 4x cubed. That looks pretty tight. I'm going to write that 4x cubed at the end. Now that seems slightly better. Let's see, the derivative of 4x to the 5th is going to be 4 times to that same x to the 5th, natural log of the base 4, and then times 5x to the 4th power. Yeah, my brain just caught like, hey, why aren't we multiplying some of these things together? And really, because, well, that 4 in the natural log is locked up in the natural log. We can't do 5 times this 4 since they have different exponents, things like that. All right, next block. Okay, here must be why I asked you to simplify. So the derivative of, that is not multiplication, is it? Sine of e to the x, or sine of something, is cosine of that something. That something is e to the x, which has a rate of change of e to the x. Some more chain rule stuff. Oh, these are all about sines, cosines, tangents, and things like that with all of these others mixed in. Okay, so the derivative, let's leave some room, of cosine of something is negative sine of that same something. That something is 2 to the x, which has a rate of change of 2 to the x natural log of 2. Well, that didn't fit. Let's make parentheses. I don't really know what order is better here. So I know I'm going to have a chain rule, 3 to the x natural log of 3, and the derivative of tangent is secant squared, still with 3x in there, right? So I'm just writing my chain rule out front, trying to save some writing. Wonder what my old solution guide looks like. Did I rewrite that? Oh, that's a different one. Oh well. Okay. The derivative of secant, let's go slow on this one because I know some people are going to write it wrong, is going to be secant and tangent, and each of those have a 4 to the power x as the input. Chain rule times 4 to the power x, natural log of 4. Which means now we can do cosecant of, or the derivative. So that's going to be negative. I'll do my chain rule first. 5 to the x, natural log of 5. Cosecant of 5 to the x, cotangent of 5 to the x. The derivative of cotangent of something is irrelevant. 6 to the 4th power is a constant. Cotangent of a constant is another constant. Derivative is 0. All right, that block went quick. Cool. Can I? Yeah, okay. Make sure I didn't miss anything. Okay, here come the logs. So the easy one is the derivative of natural log of x, 1 over the input. The way I say something like this is the derivative of natural log of something is 1 over that something. That something is x squared, which has a rate of change of 2x. So we can finally get a useful simplification. So here, dy dx is, hopefully you know we're going to get 3 over x, or at least I think we are. Derivative of natural log of something is 1 over that something. That something is x cubed, which has a rate of change of 3x squared. and so we get 3 over x. So here you should be thinking derivative of natural log of x to the 4th should be 4 over x. Let's see, 1 over x to the 4th, chain rule for x cubed. And we do indeed get 4 over x. Well, that's a nice little pattern. Is that always going to be the case? You could assume it is, and if you want to prove that, great. I suppose if I'm making a solution guide, I shouldn't jump over anything. Ooh, okay, so let's rewrite this just to make sure. This is natural log of x squared. And so we're going to deal with that chain rule first, 2 times natural log, and then times 1 over x. So I'm just going to write that x in the denominator. And if we want to be fancy, we should probably get rid of that 2 out front and write this as natural log of x squared over x. Alright, so what happens here? Well, that's going to be 3 natural log squared of x over x. And so maybe we want to write that natural log of x cubed squared over x. Oh man. Did I lose a 3? Oh, no, I moved it. That makes sense. So can I do it? What's this going to be? So this is going to be 4 natural log of x cubed. Cubed? Over x? That's my guess. Okay, let's see. Oh, that's... I was not thinking clearly. Well, suppose you only get that if you watch it. Okay. I'm not going to rewrite that because I don't have much room. Alright, much easier. Derivative of natural log of 5x is going to be 5 over 5x. Sorry. 1 over that input, which has a rate of change of that input. So we do get 1 over x. The derivative of natural log of 8x is going to be 1 over x as well. 1 over the input. That input is 8x. Chain rule times 8. And hopefully you're noticing that when we do natural log, we get the input in the denominator, and then chain rule the derivative of that input in the numerator. And, well, we can tell if we factor an x out of the denominator, we're not going to be able to divide anything anyways, but heck, might as well. Alright. Everybody complains about 50 problems, but I'm at 13.5 minutes. Okay. So the derivative of log base 2 of x is kind of like the derivative of natural log. We just get the extra natural log of 2 in the denominator. Don't forget, we can think of this as natural log of x with a change of base formula over natural log of 2. Okay, so the derivative of log base 3 of x is 1 over x natural log of 3. Chain rule, derivative of, let's see, log base 2 of x plus 3 is going to be 1 over that x plus 3, natural log of 2 down there, and then times the derivative of x plus 3, which is 1. Uh-oh, is the pen dead? Backup pen. That's super weird. Maybe if I save, I get to use it again. Let's try again. No, just dead. Have to charge. Okay. Fun while it lasted. Okay. Derivative of log base 3 of x squared. Well, 1 over the input natural log of 3. The input is x squared, which has a rate of change of 2x. And I suppose I could move that 2 to the denominator and put it inside the natural logs exponent, but that seems crazy. So 2 over x natural log of 3. Log base 2 of x to the 4th. What's going to happen there? So 1 over the input, natural log of 2. That input is x to the 4th. So chain rule for x cubed. dy dx is 4 over x natural log of 2. So I assume this is going to be 5 over x natural log of 4. Let's see. So 1 over x to the 5th, natural log of 4, 5x to the 4th. 5 gets left over in the numerator, x in the denominator, natural log of 4. Nailed it. All right, natural log of e to the x, that's actually pretty easy. That's just 1. The derivative is 1, sorry. Y is equal to x, and then dy dx is 1. Don't forget natural log and e are inverses. So in this direction, natural log and e are inverse, or e to a power are inverses. So we get 1 here. By the same logic here, log base 2 of 2 to the x is equal to x, so dy dx is again 1. 2 to the power log base 2 of x is also going to be 1. If you're not getting it here, these are not derivative problems. These are, hey, you know that logarithms and exponentials are inverses. That's what's going on here. And I suppose that's a nice way to end. Why is there another page? Ooh, fun. Blank page.